Good morning everyone. So today we are going to discuss about one more materials, that is functionally graded materials. As we know that there are many monolithic materials. So monolithic materials have a limitation that all the properties cannot be get in a singular material. So the same thing, the pure materials are monolithic materials. So pure materials have limited applications. So in engineering we require many properties. So depends upon the functionality of the application of the component, we need different properties. So but the pure materials are having limitations, are having limited applications in engineering due to the demand of different properties during their functionality requirements. So during the regular use, the properties, the component properties should be different. So those cannot be achieved by means of monolithic materials. So for that purpose, to overcome this property deficiency, we are mixing two or more materials. So one more thing, need for materials with different properties. So as we know that the monolithic material should have only one good property. It might be one of the mechanical property, or one of the chemical property, or one of the structural or thermal or electrical properties. Monolithic materials are good in one or two properties only. So the thing, materials with different properties. So for application we need different properties. So we need the materials with different properties to perform optimally under the service conditions. So under the service conditions, the components should work more efficiently. So for that purpose, we need different properties. So such properties are not existing in monolithic materials. So the same thing, if we want toughness as well as wear resistance, both the things cannot be possible on a single component. So such properties are not existent or difficult to obtain in a pure metallic materials. So monolithic materials, it is very difficult to obtain in monolithic materials. So therefore, what we are doing is we are mixing two or more materials at microscopic level to form a substance. Those are called alloys. So to obtain or to satisfy the desired application, we are mixing two materials which are having different properties to satisfy those applications. So here, therefore, two or more. So depends upon the application. The property might achieve by means of two materials or by means of more materials. So if in steel we are adding, main thing is iron. Along with that we are adding cobalt, manganese and nickel, etc. So these are due to improve its the properties. So one is to improve the corrosion resistance, one is to improve its wear resistance, one is to make it more tougher. So like that, every metal is having their unique property. So to get the desired property, we are mixing two or more different materials. Mixing two or more different materials, each of which possess one of the required property. So as we know that all single monolithic material should not have all properties. For that purpose, to satisfy the desired application, we are adding a different materials which are having that property, one of the required property for optimum performance, for good performance, are combined to produce what is known as alloy. So the combination of two or more materials is called alloys. So to satisfy the desired application, it means to get the desired properties for optimum utilization or for optimum performance, we are adding two or more materials to get a desired alloy. So desired materials, that is called alloy. So though we are having alloys, it means the combination, all the combinations cannot be possible. So one material is good in its thermal properties which are at 1200 degrees centigrade, whereas other material are good in its structural properties. It might be at 400 degrees centigrade. The combination of these two metals cannot be possible due to thermal equilibrium conditions. Those two combinations, why? Because those are having two different melting temperatures. Due to the properties, due to its melting temperatures, those two cannot be mixed. So those are the drawbacks of alloys. So the drawbacks such as thermodynamic equilibrium, limitations and thermal similarities and the thermal dissimilarities between alloy materials. So due to the variation in its temperatures, it means its thermal conditions. So those two, some few metals cannot be mixed. Some metals cannot be mixed. Only a few metals can be combined together to form an alloy. So, but the properties are varying. So, depends upon the application, the properties are varying. For that purpose, we need to add two different materials which are having two different properties. But to combine those two metals, it is not possible because of this thermal equilibrium. So, to overcome this, we prepared one more materials. Those are called composites. So, composites are designed to obtain different properties than the parent materials. So to get the desired properties than the parent materials, it means the monolithic materials, we are combining two materials. So as we know that the composites consists of reinforcement and matrix. Minimum two substances are required. So to get the desired property, we are mixing different materials. So though the components can satisfy or overcome the disadvantages in alloys, they are also having some drawbacks, that is delamination. So the drawbacks of the composites are delaminations. This delamination is due to high coefficient of thermal expansion. Due to high coefficient of thermal expansion. As we know that our composites consists of two materials, that is the reinforcement and one more is matrix material. So first assume that this is the reinforcement material and this is the matrix material. Those two are joined together to get the desired functionality. So these matrix materials should have different expansions and this reinforcement is having different expansions. Coefficient of thermal expansion is different for these two materials. So these two are bonded together. So due to increase in temperature, one material tends to expand more than one more thing. So but these two are interlinked by means of some bonds. So one material, this matrix material or reinforcement material wants to move, wants to expand or contract, but the other material is not allowing to move further. So these two are binded together. So this material, the upper material is having high coefficient of expansion. So with rising temperature, it would tends to move more than the lower one. So the lower one is reinforcement and the upper one is matrix. Just assume for some time. So this material want to move more than these reinforcements, and this reinforcement is not allowing to move the matrix material, so that the internal stresses will be developed inside the component, so that the performance will be reduced. So if there is the weak bonds between these two, then the reinforcement and fiber will be mismatched. The reinforcement will move longer than the matrix material or vice versa. So depends upon its original properties, the material can move more than the other material, so that the bonding between these two will be damaged. Those damage is called delamination. So due to its thermal expansion, due to the high coefficient of thermal expansion, this delamination will take place. Why? Because here we are using two different materials. These two different materials are mixed physically and chemically at different properties. So these two are not mixing together. So it's not soluble in each other. So those two are different materials. So reinforcement is separate and matrix materials are separate. So those two are bonded together. So whereas in alloys, those two are microscopically mixed together, where here in composites, those two are different materials and those two are joined together. So due to expansion or due to rising temperature, one material will tends to expand more than the other material. So due to this, the material will expand more, so that the bonding between these two will be damaged, so that the delamination will take place. Imagine two materials. So this is the total composite material. In that composite material, we are having different reinforcements. So the shaded one, these lines are fibers, and the remaining blue color is our matrix material. So here there is a bonding. There is bonding between these two materials. So this reinforcement is bonded with the adjacent matrix material, and imagine this is the bonds between the reinforcement and the matrix material. So here the matrix material So the blue color, the matrix material is having some coefficient of expansion, whereas this reinforcement, the fibers are having different coefficient of thermal expansion. So due to rising temperature, the fibers want to move more than the matrix material. So here, with the rising temperature, the fibers would like to move. It means expand. Whereas due to reducing temperature, it may contract also. So it means it want to change. But those are interlinked. Those are bonded with the matrix material. So this fiber would tends to move either expansion or contraction. But the matrix material is not allowing to move. That's the case. So if further the reinforcement wants to move along, so then the bonding between the matrix and the reinforcement will be damaged. So that the fibers will be easily peeled off from the composite material. So here the fibers move more than the reinforcement material, so that the bonding between, so imagine these are the two materials. So imagine this is the matrix material and this is the reinforcement material. These two are bonded. So these two are bonded. So the next case, with rising temperature, the matrix will retain its original position, but the reinforcement wants to move more, so that the bonding will be damaged. So it's want to move. If the reinforcements further moves more, then these bonds will be damaged. So that if these bonds are damaged, then there is a separation between the matrix and the reinforcement, so that the delamination will take place. This is only the delamination. The component will be delaminated from the main portion. The reinforcements are delaminated from the main portion. So this is due to the thermal expansion, high coefficient of thermal expansions. The next one, these challenges among others have led to the development of unique materials known as functionally graded materials. So those are also called as FGMs. So as we know that, as we discussed that the alloys are having some drawbacks, whereas the composites are also having drawbacks. So to overcome these drawbacks, we designed a unique material that is known as functionally graded materials. That is called as functionally. So it depends upon the functionality. The materials will gradually varies. So that is functionally graded materials. That is FGMs. Functionally graded materials. So functionally graded materials are specialized type of advanced materials. These are advanced materials than the composites and the alloys. So developed to withstand and serve. So these are developed to withstand and serve severe conditions. And to withstand service conditions while performing at optimum during its service. So during the application, the component should perform give optimum properties. For that purpose, we design a different materials that is called functionally graded materials. So they are developed such that, so these functionally graded materials are developed such that the their properties and their composition and the features of the constituent elements of the material varies with respect to. So if we consider this a composite material, functionally graded material, we consider this FGM. The materials, the properties. So here, if we test the properties at different locations, the properties will vary. Why? Because this is the composition of our component. So if you observe that there are many black spots compared to at the bottom. So from left to right, so the black spots are reduced, so that the white area is increased. Here the composition of different other material is high and here it is low, so that the property will vary from one direction to other direction. So one property might increase in this direction, other property will decrease along this direction. So depends upon the application. The properties will vary from one location to other location. So these materials are developed such that the properties, the composition. So here the composition is varying. So if you observe that maybe the graphite particles are higher here. If you consider one material, so if you consider an example of copper and titanium. So here the titanium particles are more compared to the first portion. So if we segregate this component into 4 parts, so 1, 2, 3, 4. So the composition at first portion and the composite in the last 4th portion is different. So here the titanium, maybe if we consider the black spots as titanium, the titanium particles are less, whereas here those are more. So due to variation in the titanium or the different material, the properties will vary. So they are the features, that the properties, the composition and the features of the constituent elements of the material varies with respect to the location and the dimension. So with respect to location, so if we consider this as 0, 0, from here to here, the location, with respect to the location, the properties will vary. Along with that, with respect to the dimension of the component, the properties also varies. So now here, due to this FGM, due to the variation in properties or the variation in the composition, the sharp interface with, so here it is replacing the sharp interface with gradient interface. So first thing, so functionally graded materials. So what is the purpose of this? So functionally graded materials. So depends upon the application, we require 2 different properties on different sides. For example, if we consider our door, so our door is made up of wood and that is surrounded with a sunglass. So sunglass is used to protect from environmental conditions, from moisture, from sunlight and all, so that the life of the wood is increasing. It means the durability of the component will be increased. So here the monolithic material, the wood as well as the sunglass cannot perform for a long time. So if these two are mixed together, then the performance or the durability of the component will be high. Why? Because the wood, so the bare wood cannot withstand for a long time. Because if it is exposed to the moisture, the material will swell, so that the properties or the strength of the material will be reduced. So whereas the sunglass, the protective sheet of the door, the sunglass, if we prepare the complete door with the sunglass is a brittle material. It easily breaks. So that the material, if those two materials are identical, the property, the durability of the component is less. So to overcome this, to make the material for a long time, to increase the durability, we are joining together so that the background, the wood gives the required strength of the material and the outside the sunglass will provide protection from the environmental conditions. So here the wood and the sunglass, so that our component, our application, the desired application is satisfied, so that the life of the component will be more. It means the durability will be high. But the condition is, so here there is a sharp interface between these two things. It means these two are joined. So this material is having different expansion, whereas this sunglass is having different expansion. So due to having different expansions and contractions, the materials will expand so that the bonding between these two materials are damaged. That is only the sharp interface. So imagine this, one is the wood and one more is glass, sunglass or veneer. So these two are joined so that there is a sharp interface. So whereas here in FGMs, the interface is damaging, is different, is changing. So here this wood may have thermal expansion of 10 mm, whereas this is having 1. The unit is 10 and here the unit is 1. So the wood moves more than the above material. So due to that, the bonding between these two will be damaged. So this is due to the sharp interface. Whereas here in our FGMs, the material. So here we mixed two materials, that is considered as copper and titanium. So here in the first portion there are more copper materials, so that the expansion will be, so imagine the copper metal is having an expansion of 10 and the titanium is having 1. So similarly the same conditions, if we consider two materials, so one is titanium and the one more is copper. This copper is having a thermal expansion of 10, whereas the titanium is having 1. 10 and 1. So if there is a rise in temperature, the titanium will not move further, whereas the copper will move more. So that there is a sharp interface. So there is quite a difference. There is a high difference between these two expansions, so that the two components will be separated from each other. So whereas, so this is a regular alloy, or this is a regular bonding. So whereas here in functionally graded materials, in FGMs, so first component is having 90% of copper and 10% of titanium. So that here the expansion will be 9. So further the titanium is increasing, so that the expansion will be 8. So that here it is 7. So here it might be 6. Gradually the interface is changing. So whereas here this is having 10 and this is having 1, there is a sharp interface between these two. Here gradually, due to variation in compositions from one side to the other side, gradually the composition is increasing. So if you observe here, the titanium particles are less compared to the next sections. Here the titanium material are increased, so that the overall expansion will be less. So from here to here it is gradually changing, whereas here it is at a time it is changing, so that the delamination will take place. So now our functional graded materials replaces the sharp interface. So these FGMs, it replaces the sharp interface with the gradient interface. So this gradual interface or gradual changing is called the gradient interface. So it replaces the sharp, replaces this sharp interface with the gradient interface. Replaces the sharp interface with gradient interface, which provides smooth transmission. So which provides the smooth transmission from material to the next material. Whereas here at a time there is a change in two materials, so that delamination will take place. Here in functionally graded materials, the transmission from one material to other or one portion to the other is smooth. Why? Because the titanium particles are increasing and copper particles are reducing, if that is a copper titanium material. So our one material 1 and material 2, due to variation in its composition, gradually the transition is, or the interface is gradual, so that the component will not be delaminated and it gives two performance. On one side it may be having high refractoriness, and one side it may be having high toughness. Here the material is also same. Here these are having high hardness, whereas here these are having high refractoriness. One side it is having high toughness. This side this is having high toughness and this is having high refractoriness. So it depends upon the application. It should have two different properties. Or one side, if it is exposing to high temperatures at that location, it should have high refractoriness. Whereas the other side, it should have high toughness. So to attain two different properties, we join two different materials. So joining of two dissimilar materials is called cladding. So here we cladded two materials, but here in functionally graded materials, we optimize the property from one direction to the other. It means gradually the properties are varied, so that the sharp interface is avoided, so that due to the expansion also the materials will expand and the expansion will be varied gradually.